Hello, Thomas. Thomas will be online today.
Yeah. It's nice for the once in a while that you just cannot make it.
Yeah, I used Zoom yesterday. So I had a meeting right before class, but I couldn't leave my house. to do the meeting.
Actually, I think there are nine students registered in this course, and all of you attend the lecture here in the class. But I am keen to keep share Zoom link for each lecture. As you know, you may be not able to attend the lecture one day, so you can attend it through Zoom. I also record the lecture and upload it.
Yeah, that's nice.
Yeah. Okay. You are welcome. Oh, yeah. Okay. No. So it's 8 p.m. now. So let's start. Good morning, everyone. Morning. Yeah. At first, I want to let you know that you have assignment raqam 2, assignment number 2. This assignment is about how we can make congestion control. Okay, so the same way as in assignment 1, you will have to read around 3 or 4 pages from certain reference and answer the questions. Okay, the due date of this assignment will be next week, Wednesday, October 6th at 8 p.m. before the start of our lecture. Okay, this is clear for you? Okay, let's start our lecture today and take this example about Bellman-Ford algorithm. Yeah. So please check your assignment section. You will have assignment number 2. The due date of this assignment will be next week before the start of the lecture. Okay. Okay. So Now, let's take this example as a revision about the Bellman-Ford algorithm. Okay, so we have 4 nodes. Node 1, 2, 3, 4, and node 1. Okay, as you can see here. Okay. For the cost of this link, 2, 1, 3, 1. And we want to find the minimum path from the source, which is node 1, to the destination, which is node 4. What should we do? Okay, discussion. Okay, so yeah, we have our tables. We have node 1, 2, 3, and 4. And here, number of iterations. Iteration 0 at first. No node can reach to the destination. So the path cost from node 1 will be infinity, and the destination node will be -1. -1 means that no destination node. Okay, and for node 2 also infinity and destination -1, and 3 will be infinity and destination -1. For node 4, as node 4 is the destination node, its path cost will be 0, and the destination node will be 4. This is our first iteration. In the second iteration, which is 1, can node 1 reach to the destination? So it is still infinity -1. What about node 2? It can reach, yeah? So what is the cost of the path from node 2 to node 4, which is the destination? 3. So we will write it as 3 plus the path cost for node 4, which is 0. Okay, so it will equal 3, and the destination node will be 4, right? What about node 3?
Two options.
Two options. Okay, so how can it reach?
Take the minimum path, so
The minimum between. Okay,
so 1 plus 3 plus 0, I guess.
1 plus 3 plus 0?
Yeah.
No,
1 plus infinity.
1 plus infinity, because 1 plus infinity, okay? Because
Oh, yeah.
this one, and you check the path cost from the previous iteration. In the previous iteration, the path cost from node 2 to node 4 was infinity. So you will add 1 plus infinity. Okay, this is clear for you? Clear? Okay. What about the second way to reach from 3 to 4? 1, which is the cost of this link, plus the path cost to node 4, which is 0. So the result will be 1, and the destination node will be 4. Clear to you? And for sure, for node 4, it will be 0 and 4. And now let's have the third iteration. Okay, so node 1 to reach to node 4, how many ways? 2 ways. So we will select the minimum between the first root is
Node 2.
so node 2. Okay, so what is the cost of this pass? 4, which is the cost of this link, plus the path cost from node 2. So node 2 from our previous iteration was 3. So 4 plus 3, which is 7. What about the second root?
Through node 3.
Through node 3. What's the cost of this path? 2 plus 1. So 2 plus 1, which is 3. So the minimum will be this path. So this will be 3 through which node? 3. Okay. What about node 2?
Same as last.
Same as last. Okay, so node 2 has only one way to reach to destination 4, so it will be as the previous iteration 3, 4. Okay, and for node 3, the same. Okay. And this is node 4. So, and if we repeat for fourth iteration, you will see that we have convergence, no change in the path from node 1 to node 4. So in order to go from node 1 to node 4, we have to go to node 3, 1, 3, and 4. Okay, so we'll go through this way. 1, 3, 4. This is the path with the minimum cost selected based on using the Bellman-Ford algorithm. Okay, and we said that each node or each router must build its own routing table. Okay, using Bellman-Ford algorithm, each node is interested only in the networks that it can reach. For example, node 1 can go to node 2, can go to node 3, can go to node 4. Okay, so in the routing table of node 1, it must include information about its network, okay, and network 2, network 3, network 4. Okay, for node 2 can go to which node? 4 for only. Yes, so its routing table include information about its network and node 4. For node 3, it can go to which node?
2 and 4.
2 and 4. So the routing table of node 3 will include information about its network, node 3, and network 2 and network 4. And as you can see, the routing table include the node ID, the destination node, the cost to reach to the destination node, and what is my exit interface. For example, okay, here for node 1 to go to node 2, okay, so node ID, node 1, destination node, node 2. It will go with cost 3. The next node or the next interface will go through node 3. So it will go from 1, 3, 2. Okay, so as you can see, each node is interested in its network and the networks that it can reach. Okay, so following this way, we are minimizing the size of the routing table. Okay, so as in the default ways, the routing table must include all information about all the networks. Okay, but in this case, we are interested only on the node that we can reach. Okay, so when we minimize the size of our routing table, so we minimize the required memory to be installed in this router. So we are minimized the cost in terms of money or budget, okay, of this router. So simple routers with limited resources, okay, it's better to use Bellman-Ford algorithm in building its routing table, as Bellman-Ford algorithm helps the routers to minimize the operations required, minimize the size of routing table, minimize the resources required. Okay, so this is one of the advantages of the Bellman-Ford algorithm. Actually, Bellman-Ford algorithm is used in practical or in commercial cases in distance vector protocols, which like RIP, Routing Information Protocol, and EIGRP protocol. Okay, so for distance vector protocols, whose metric is minimizing number of hops, it's better to use Bellman-Ford algorithm. This is clear to you? Okay, that's perfect. Now, let's introduce the Dijkstra algorithm. Actually, the Dijkstra algorithm is also one of the important algorithms to determine the way from source to destination with minimum cost. But it is unlike of Bellman-Ford algorithm. This algorithm requires huge processing capabilities. As for here in Dijkstra algorithm, each node will be interested in all other networks. So the size of your routing table will be very large. So you need to make huge processing. So you need routers or networking nodes with high processing capabilities, which means that you need routers with high cost, pay more money. Okay, so let's understand the Dijkstra algorithm through introducing this example. Okay, as you can see. Okay, so in this example, we have node 1, node 2, node 3, node 4, node 5, node 10. Okay, so node 1 can go to node 2, node 1 can go to node 3 with cost 1 and 2. Node 2 can go to node 4 with cost 3. Node 4 can go to the final destination with cost 3. Node 5 can go to the destination with cost 1. Node 3 can go to destination to node 5 with cost 5. Node 2 can go to destination with cost 4. And node 3 can go to 4 with cost 1. And we already studied this example using Bellman-Ford algorithm. And if I asked you to tell me how we can select the path with the minimum cost using Bellman-Ford algorithm, I think it's easy to you to do it. Yeah. Let's now understand the steps of the Dijkstra algorithm. Okay. So at first we must form our table. Number of iterations. Selected node. And after that, node 1, node 2, node 3, 4, 5, and our final destination. Okay. This is clear for you? Okay. So now in Dijkstra algorithm, we start by selecting one node, any node. You can select node 1, you can select node 2, you can select node 3, 4, 5, 6, any node you can select. Okay, so we prefer to start with our source node. Okay, so we will select node 1. Okay, now we are here at node 1. Okay, so again, you can select any other node. You can select node 3, for example, if you want. Okay, but I want to go from node 1 to node 6. Okay, so it's better to start with the source. Okay, so you will select node 1. This is your first step. After that, you must calculate the cost of all the neighbors to node 1 to reach to node 1. So who are the neighbors of node 1? 2 and 3. Yeah. So I must calculate the cost from node 2 and node 3 to reach to node 1. Okay. Okay. So at first, the cost of node 1 itself, it will be 0, and the destination will be node 1. This is clear for you? Okay. Okay. What is the cost for node 2 to reach to node 1? It will be 1 plus the cost of node 1, which is 0. Okay. So the cost of node 2 to reach to node 1 will be 1 through, what is the destination?
2.
Node 1. We are calculating the cost from all the neighbors to reach to the selected node. Okay? Okay. And this is good point to highlight. In Dijkstra algorithm, we are not interested in the direction of the line. Okay, so I know that you said node 2 because the direction of the line is pointed to node 2. Yeah, in Dijkstra, we are not interested in the direction of the line. Okay, we are here calculate only the cost of all the neighbors of the selected node to reach to this selected node. Clear?
Yeah.
Okay, so the cost of node 2 to reach to node 1 is 1, and the destination will be 1. Okay, what about node 3?
Cost would be 2 and the destination would be 1.
The cost will be 2 plus the cost of node 1, which is 0, so 2, and the destination will be 1. Okay, now we have checked all the neighbors of our selected node, which is node 1. So for node 4, it can reach to node 1. So it will be, the cost will be infinity and the destination will be -1. For node 5, the cost will be infinity and the destination will be -1. In node 6, it will be infinity and the destination will be -1. This is our first iteration. This is clear for you. So in our first iteration, we select any node. Aman? Are you okay?
Yeah.
Okay, no problem. We select any node in the problem. Any node, you are free to select node 4, to start with node 4, for example. Okay, but we prefer to start with the source node if we want what is our source and what's our destination. So it's better to start with the source. And after that, after selecting one of the node, which is the source, we check the minimum cost from all the neighbors to node 1 to reach to node 1. Okay, so this is our step. The second step is to select another new node to be the current node and check all of its neighbors. Okay, but we must select the node with the minimum cost. Okay, and don't select visited node before. So we can select node 1. Okay, we are done with node 1. We have to select another node from 2, 3, 4, 5, 6. But this node must have the minimum cost. With what node should we have? Select 2. Why? Its cost is 1. We have node 3, its cost is 2. Okay, we have node 4, 5, and their cost is infinity. So we have to select node 2. So here in selected node, we already selected node 1, we will select node 2. The cost of node 1 will not change. Okay.
What if 2 and 3 have the same cost? Like what if they were both?
You are free to select any. Yeah. Okay. So for node 2, its cost is the same also, 1 to 1. And let's check the neighbors. What are the neighbors of network 2?
4 and 5.
4 and 5. Correct. So what is the cost of node 4 to reach to node 2? 3 plus, no, 3 plus the cost of node 2.
So it's technically what is reached at one.
Yeah, so we have 1 here, okay, which is the cost of node 2. We will add the cost of the link between 4 and 2. This is clear for you? So we add the cost of the link plus the cost of the node. As what we have done in Bellman-Ford algorithm. So the cost of node 3, for node 4, it will be 3 plus 1, which is 4, and the destination node will be 2.
Why are we adding 1 if we're saying the destination is 2? Shouldn't the destination be 1 if we're going to add 1 to it?
We are looking for the cost to reach from node 4, okay, to node 2, okay? Yeah, so the cost to reach from node 4 to node 2 is 3 plus 1. As at the end, you are forming the path from 3 to 1.
But so if we were looking for the destination to 2, wouldn't it be 3, 2?
Yeah.
We're looking for the destination to 1 and 4, 1.
I understand what you say. So you suggest that the cost to be 3 and the destination will be 2. This is your answer. As I'm interested to the distance to node 2. Yeah, this is what you say, okay? But after finishing this table, you will discover that you are forming away from all the nodes to 1. So 1 now is able to select what is its minimum way to reach to the destination. Okay, so at first we selected node 1. Okay, so at the second node you select node 2. Okay, but node 2 must serve to node 1. Okay, so I must add the cost of node 1 to reach, of node 2 to reach to node 1 with the cost of this link. Okay, after finishing this table, you will understand why we do it. Okay, so we will start with, so we will add 4, which is 3 plus the cost of node 2, and the destination will be 2. What about node 5?
5,2.
4 plus the cost of node 2, which is 1, will be 5. And destination is 2. Node 3 can't reach to node 2, so it will be infinity minus 1. And node 6 will be infinity minus 1. What about which node should we select in our third step? Okay, which node? Node 4. Okay, 1, 2, and 4. And why it is 4?
It's the minimum cost.
It is the minimum cost. So node 4 has 4. We have node 1 is 0, but it's already selected, so we can select again. Node 1, node 2 is 1, but it is already selected before. Node 3, sorry for that. Oh, I did mistake. The cost of node 3 must not change, as it's already 2, 1 from our previous iteration. We can't change it again. Okay?
Even though 3 can get to 2.
Even, yeah, that, yeah. So the cost of node 2, 3 can't be changed. We are selected the minimum cost. So if we compare between infinity and the cost of 2, what is here is the minimum?
Maybe 2.
2. So the only case that you change the cost is you have another minimum cost. When you compare the previous cost with the current cost, and if the current cost is minimum or less than the previous cost, you change your cost. If not, if the current case is not less than or minimum from the previous case, so your cost will remain as in your previous case. Okay, so here the minimum, we must select which node? 3. Okay, 3. So we have node 1, it's already vested, will not change. Node 2, it's already vested, will not change. And we are now at node 3, so its cost will not change. And we will check the neighbors of node 3. Who are the neighbors of node 3?
4 and 5.
Node 3 has 4 and 5, and it also has node 1. But as node 1 is already visited before, we will not check it again. Okay? As I told you, in Dijkstra algorithm, we are not interested in the direction of the link. So the neighbors of node 3 is 1, 5, and 4. But node 1 is already visited before. So we will not check it again. This is the case also was in node 2. The neighbors were 1, 4, 5. But as node 1 is already visited before, we didn't check it. We only checked node 4 and node 5. So in this case, the neighbors of node 3 are 1, 5, and 4. So we will visit only 4 and 5 as 1 is already visited before. Okay. So what is the cost of node 5 or node 4? Let's start with node 4. Node 4, it will be the link cost, which is 1 plus the cost of node 3. So it is 1 plus 2, it will be 3. And we have previous case 4 and 2. Which one is the minimum? 3. So we will change the cost of node 4 to 3. Okay.
Why did you pick 3 as your next point? Like, according to the logic you were saying before, you picked the minimum of your next destinations, but 3 is going backwards. We already said 2 is the minimum between 2 and 3.
3 is going backwards. As I told you, in Dijkstra algorithm, we are not interested in the direction of the link. Okay, so we are dealing with our network as like this shape. No arrows, no directions, no direction.
So we're just checking every single thing.
Yes. So this is our network. Yeah. This is our network. Forget the direction of the links. Okay. This is our network. Okay. So now, in order to calculate the cost of node 4, we have previous case, which is 4 through destination node 2. And now through node 3, we have destination, we have the cost will be 3 through the destination 3. We will select the minimum. What is the minimum cost? The 3. So the result will be 3 through node 3. What about node 5?
7.
Node 5 has the minimum between 5 and 2, and we have 5 plus 2, 7 and 3. So what is the minimum? 5 through 2. So we will select 5 2. Okay, and for node 6 it will be infinity minus 1. Now let's select the new node, but we will not have to select node 1, 2, 3, and select one node from 4, 5, 6, which is the node that has minimum cost. Which one is 4? 4. 1, 2, 3, 4. And the cost of node 1 will be the same. 2 also will be the same. 3 will be the same. And 4 will be the same. And in 4, what are the neighbors?
6.
We have for node 4, 2 nodes are the neighbors, node 2 and node 6. But node 4, node 2 we already visited before, so we will not check it. We only check node 6. So for node 6, what is the cost of this node?
3 plus 3, 6.
Okay, so it will be 6 and destination
4.
4. And the cost of node 5 will be the same as we compare it between 5 and 2 and infinity minus 1. So 5 and 2 is the minimum. So we'll say keep it. And now the term to select between node 5 and node 6. Which node we will select? 5. Okay, so the same. We are now at node 5, so it will be the same. Who are the neighbors of node 5?
2, 3, and 6.
Node 5, 2, 3, and 6. Okay, which one we will check?
6.
Why?
2 and 3 we visited before.
Yeah, so we only check node 6. What is the cost of node 6?
That would be 1 plus 5, so that would be 6. 6 comma 5.
Okay, so we must select the minimum between the previous case and our current case. Which one should we select?
Doesn't matter.
Doesn't matter. We can make load balancing. Okay, so okay, now I think we visited all the nodes. The last one is the node 6. But it will not change anything as all the previous nodes are already checked. So in order to reach from source 1 to node 6, we have two routes, two ways. So from node 6, we can go to node 5, and node 5 go to node 2, and the node 2 go to node 1. Or we can go from node 4, and node 4 go to node 3, and node 3 go to node 1. So we can go 1, 2, 5, 6, or 1, 3, 4, 6. Okay, this is clear for you. I take node 5. This is a destination here. The destination in node 5 is node 2. Okay, the destination in node 2 is node 1. Okay, so 1, 2, 5, and reach to the destination, which is node 6. Or I can take node 4, and the destination of node 4 is node 3, and the destination of node 6, sorry, that this here, yeah, and the destination of node 3 is node 1. And this clear for you? Clear? Not clear? Yeah. Which part is not clear for you? How to select the destination? How to select the okay. So I can this now. Based on this table, okay, this table, node 1 must make this computations. So as we start with node 1, okay, so all of this processing are done in node 1. In this case, node 1 is using these steps to calculate how to reach to all the nodes. Node 1, 2, 3, 4, 5, 6. Okay, to all the nodes. Okay, so we want at the end to know how can node 1 reach to node 6. Okay, so this is your destination, node 6. Node destination has two costs, and they are equal: 6 through node 4 and 5 through node 5. So 6 through node 5. So 6 can communicate with node 4 or with node 5. Clear to you? Okay, so return me back to node 4. Node 4 can communicate only with node 3. Okay, so return to node 3. Node 3 can communicate with node 1. So this is the way that node 1 can take to reach node 6 or node 6 can take to reach to node 1. Okay, let's take the second way. Node 6 can communicate with node 5. Node 5 can communicate to. Node 2 can communicate with node 1. Okay, this is the process done in source node 1. If you want to find the way from node 2 to reach node 6, for example, we will repeat this process, but starting with node 2. So this process will be repeated at node 2. Okay, if you want to know the way from node 3 to node 6, we will repeat this process and start with node 3. Okay, and repeat all of these steps. So as you can see, the processing computations done using Dijkstra algorithm is very heavy, it's very complex, but at the end, it enables each node to know in order to reach to any other node in the networks, in our large network, I can know the route. Okay, so for example, if node 1 want to go to node 3, so in NAS, I can go to node 3 in direct way. For node 1 to go to node 4, it can go from 3 and 1. Okay, and for node 1 to go to node 5, it can go from 1 to 5. So at the end, node 1 know what is the minimum cost to reach to all other nodes in the network. To all other nodes in the network. Okay, so network 1 know now the topology of the network. So if we ask network 1 to plot or draw the topology of the network, node 1 is able to draw the topology of the network as its routing table include all the required informations to reach to all other nodes in the network. So this processing is very complex to the router to do. And here we have only 6 nodes. What if we have 10? What if we have 20? What if we have 50? What if we have 100? It is very complex process. And at the end, the router must do this processing at very high way, at very high speed. So this algorithm requires high processing capabilities. So it is used in link state protocols like OSPF. As I told you, OSPF is the most popular routing protocol used now in the industry. And OSPF, it requires the routers to know full topology of the network. Remember, in Bellman-Ford, each router is required to know the networks that it can reach only, not all other nodes. Okay, I'm not keen about all other nodes. Okay, but here in OSPF, each router is required to know all possible information about all other networks. So you need large memory to store all of the required information. Okay, so this was we discussed this example. You can do this example as exercise at your home to check if you remember, if you understand the Dijkstra algorithm in correct way or not. And these are final remarks about the Bellman-Ford and the Dijkstra. As here, Dijkstra algorithm requires knowledge of all lane costs in the network, global knowledge, full network topology, okay, but allows nodes to compute minimum cost buses to all other nodes. In Bellman-Ford algorithm, this distributed algorithm, it requires local knowledge of network information. Okay, so each node knows the next hop to destination via minimum cost bus. Okay, here, as I told you in our first lecture, cost can be the minimum number of hops, can be the delay, can be the speed, can be any other metric that you can consider to find the best way based on your criteria. So you can create your own routing algorithm, determine one criteria. This is your cost, and you want to minimize or maximize this cost. For example, if you are dealing with speed, so I want to maximize my cost. I will select the way with maximum cost, not minimum cost, as I want to select the route which is the fastest one or higher speed one. Okay, but if I want to minimize the delay, I want to select the route with minimum cost, for example. So cost again here means different metrics that you can select, and we discussed different metrics before. Some of you told me delay, number of hops, speed, and many other congestion control. Different metrics can be considered. Okay.
In the real world, are these networks considered pretty static?
In what?
In like the real world, are these networks considered quite static?
Static routing protocol?
No, like the nodes don't change a lot. Like you only see 2 go offline very often, or node 3, so you can just keep the table for like in hard memory.
Yeah.
Or is this more so done on like RAM?
Okay, actually, this routing table is changing over the time. It is not fixed, it is not static, okay? Because the network may have failure, for example. Maybe this link failed. Yeah. So if this network is failed, so there is no connection to node 3, okay? So in this case, node 1 will not make load balancing. So this bus has failure, so I will forward all my packets through this way. Okay, so all the nodes must update all other nodes in a regular way. We must send periodic messages about, hey, my routing table now is that. You exchange me, yes, I will update you with my routing table. Even no change happens. So for example, every 5 minutes, we will exchange together our routing tables to confirm that no change happened in the network. And if any change happens in the network, through exchanging these routing tables in a periodic way, we can discover, yes, there is a change happening here, and I must remake or redo our calculation again. So I will recalculate my calculation again to update my routing table. Okay, this was your question about or not?
Yeah, I was just wondering if like this was if the routing tables were stored more in like hard drives or something.
Yeah, you can. Yeah. The router is like computer. It has flash memory, it has hard disk, it has processing, it has RAM, installed RAM. Okay, it has the operating system. Okay, so all you are dealing with the router as it is your personal computer, but it has high processing capabilities. So yes, this routing table is stored in the hard disk of the router, okay? And it can access this routing table, and for sure, in every routing process, it will access to the routing table and check how to reach the destination. Should we update our routing table? So yes, this routing table is stored in the memory of the router that the router can access and change and update, move or delete. Deal with the router as personal computer with all the capabilities of the computer. Flash memory, hard disk, RAMs, CPU. Okay. So yeah, this is correct. We are done now today about routing algorithms. We understand now how we deal with Bellman-Ford algorithm, which is used in distance vector protocols, and Dijkstra algorithm, which is used in link state protocols. Anyone has any question? Please do this example at your home. And if you have any problem, we can discuss in our next lecture. Okay? Have a nice day. Thank you, Thomas. Okay, bye.